Hello, students. I am here to do for you a weak acid, strong base titration. This is the problem that you guys are working on in your groups in class. I'm going to go through it super slow through each step. So if you made a mistake along the way, just make sure that you slow down at that part and make sure you figure out what exactly happened that led you astray. So I'm going to try to walk through or talk through each step of the process. And I'll go ahead and share the whiteboard to tell you about this problem. So the first thing is the basic information. They say that we're starting with 80 milliliters of 0.1 molar formic acid. So we'll just call this HA for our weak acid. And we're titrating with 0.2 molar NaOH. And they gave us some additional information. They said that the Ka for our weak acid is 1.77 times 10 to the minus 4. Okay, now there are 6 parts to this question. The first part is not actually necessary, but we're going to do it because it helps us orient ourselves for the rest of the question. And that is, what volume of NaOH is needed to get to the equivalence point? Now, this is super helpful for us because if we know when the equivalence point is, we're also going to know when we are before or at or after the equivalence point. And that helps us frame our mindset so we know what way we have to attack the problem. Before the equivalence point, we know that the acid is in excess, the base is limiting. After the equivalence point, we know the base is in excess. Before the equivalence point, we know we're going to have a buffer system because this is our weak acid titration. At the equivalence point, we know that we're going to have just a conjugate base. So orienting ourselves to how much, where we are in the course of the titration is really important to just help us keep track of what's going on and what our plan of attack should be. So the first thing that we're going to do is we're going to use this sort of shortcut equation. The concentration of our acid times the volume of our acid equals the concentration of our base times the volume of our base at the equivalence point. Now, this only works for monoprotic and monobasic acids and bases, so just be careful if you've got some stoichiometry going on, like you have a CaOH2 in there or something like that, just make sure you account for that, and this equation might not work for you. Okay, so we know we've got 0.1 molar acid. We know the volume is 80 milliliters. And for our base, we know it's 0.2 molar, but we don't know what the volume is going to be. So we can solve for the volume, and it's going to end up being 40 milliliters. So that's how much base we have to add to get to the equivalence point. So in all the questions that are following, if we're before 40 milliliters, that means the acid is still in excess. If we're after 40 milliliters, we know the base is in excess. So that's just a good sort of orientation to what's going on. Now, the second part of the question is, what is the initial pH of our acid solution? And for this one, because we've got a weak acid, our formic acid is a weak acid, and what do weak acids do? They just react with water to make hydronium and the conjugate base. That's the Ka reaction. So I'm going to write that reaction out. We've got our weak acid. It reacts with water. It's an equilibrium reaction because weak acids are always in equilibrium. We're going to get our conjugate base, and then we're going to get H3O+. So that's our reaction. And our initial concentration here is 0.1 molar. We always use concentration in our rice tables and moles in our BCA tables. So here we've got a little bit of this is going to dissociate. It's going to make some of the conjugate base. It's going to make some of the H3O+. And we're going to get Ka equals 1.77 times 10 to the minus 4. And that's x squared over 0.1 minus x. It's close to the cutoff here, but I've got 3 orders of magnitude difference, so I'm going to neglect my x. So I'm going to get 1.77 times 10 to the minus 5 equals x squared, and x equals 4.21 times 10 to the minus 3. And x is the same as my H3O plus concentration. So if I take the negative log of that, I'll get my pH, which is 2.38. So that's my pH at the beginning before I've added any of the base. Now, key things that you need to note that we did here. The first thing that we did is we identified what was the thing that we had in our beaker. And we said, this is a weak acid. What do we know about weak acids? What do? They're going to react with the base that happens to be around. Water can be a little bit like a base. It's neutral, right, by itself. But it's amphoteric or amphiprotic, meaning it can act as both an acid or a base. And in this case, it's the only thing around that acid can react with. So that's what it's going to do. But because it's a weak acid, it's only going to do it a little bit. It's going to be an equilibrium reaction. So if I have a weak acid and it's sitting in water, the thing that it's going to do is this right here, our Ka reaction. And this is in fact a generic form for the Ka reaction for any weak acid. Okay. So we've got our weak acid reaction. That's the first and important part. The second thing is we know it's equilibrium. And when it's equilibrium, we're going to use our Rice tables. And so both of these things go together with the idea of it being a weak acid. Weak acids are going to do this Ka reaction, and it's an equilibrium reaction. So we do the Rice table. Okay, now part C of our question is going to ask us, what's the pH after adding 20 milliliters of NaOH. And this is where we're going to be grateful that we asked first, how much do we need to get to the equivalence point? Because 20 milliliters is something called the half equivalence point. It takes 40 milliliters to get to the equivalence point. So 20 milliliters would be our half equivalence point. And it turns out when you've neutralized exactly half of the acid, then you have equal quantities of acid and conjugate base, right? If you started with 1, half of it is gone. So this would be like 0.5, and half of it gets turned into our conjugate base, and that would be 0.5. So at the half equivalence point, we know that these two are equal. And if that's true, and we use our Henderson-Hasselbalch equation, pH equals pKa plus the log of the conjugate base over the acid, and we know at this point these guys are equal, that's the log of 1, that's 0. So my pH just equals the pKa. And if the pH equals the pKa, all I have to do is the negative log of 1.77 times 10 to the minus 4, the Ka value that they gave us before. And I get my pH equals 3.75 after 20 milliliters of NaOH have been added. So could we have done this the other way? We could have also just written out our BCA table. We've got NaOH, so we'll have our OH minus reacting with our weak acid. It's going to react stoichiometrically. And we could fill in our whole BCA table here. And what we would end up with at the end is equal quantities of our HA and A minus. So let's just do it for kicks. We've got here for our HA 0.008 moles. And because we're adding 20 milliliters of the 0.2 molar NaOH, this would be 0.004 moles. It reacts stoichiometrically. All of our base is going to get used up here. And we end up with equal quantities of our weak acid and its conjugate base. So when we get to this point, we would plug this into our Henderson-Hasselbalch equation, and that would put us right here. Okay, that is the first 3 parts of the question. Now, the next part of the question is what's going to happen after adding 35 milliliters of NaOH. So this is still before the equivalence point. So we're going to be kind of in the buffer region of that titration. So we haven't reached the equivalence point yet. So now what we're going to do, we've got our strong base that we're adding to our weak acid. We know they're going to react stoichiometrically. How do we know that? We're adding something strong. We always have to deal with a strong thing first. It's going to react with whatever is there. OH minus is our base. It's going to react with the HA. Stoichiometrically, we're going to get water and we're going to get A minus. So again, we were starting with 80 milliliters of 0.1 molar formic acid. So this will be 0.008 moles of our HA. And at 35 milliliters of our 0.2 molar, this is 0.007 moles of OH minus. So again, these react completely. Our base is still limiting. We're going to end up with a mixture of weak acid and conjugate base. That is, in other words, a buffer, as long as these are within a 1:10 ratio. So we're pushing the limits here because this is a 1:7 ratio, but it should still be okay. And we're going to use our Henderson-Hasselbalch equation, pH equals pKa plus the log of 0.007 over 0.001, our base over our acid. Now, I do want to point out, these should be concentrations. I'm just putting in the moles here because the volumes are the same for the top and the bottom and they cancel out. So because it's a ratio, I can put it in this way. But remember, anytime you're done with your BCA table, these are always in moles, not molarity. Okay, so our pKa was 3.75. And then we're going to have the log of 7, which is 0.845. And we get 4.60. So that is our pH after we have added 35 milliliters of NaOH. Again, what are the things that we did here? First, we recognized we had the strong base and the weak acid. So they're going to react with each other and they're going to react stoichiometrically. So we wrote out our reaction here for what would happen when we mixed that strong base with a weak acid. We used the moles to get the BCA table. And we found out at the end of your BCA table, you always have to reevaluate and say, what do I have now? And we saw that we had a mixture of a weak acid with a conjugate base, which is a buffer. So we knew that we could use the Henderson-Hasselbalch equation. You could have also at that point chosen to do a Rice table. The Henderson-Hasselbalch equation just gives you kind of like an easier way to do it if you know that you have a mixture of the weak acid and its conjugate base. Okay, so my pH is 4.60 after 35 milliliters of NaOH have been added. I'm just going to check my thinking here. I know in my buffer, I had more of the conjugate base than I did of the weak acid. So it makes sense that my pH would be a little bit higher than the pKa, and we do see that. So this is an answer that makes sense. Okay, let's move on to part E. In part E, we're asked, what's the pH at the equivalence point? Okay, at the equivalence point, there's kind of two ways that we can go about doing this problem, a short way and a long way. I always like to tell you the short way and then I'll show you the long way. The short way is to recognize, to know, at the equivalence point, 100% of our acid has been neutralized and it will have been converted into our conjugate base. So that means if I started with 0.008 moles of HA, when I get to the equivalence point, it will be 0.008 moles of A minus. Okay, now the long way to do that is to say, okay, I'm mixing together my strong base and my weak acid. So I've got OH minus and HA, and we're making H2O and A minus. And I've got 0.008 moles. This is our BCA table of each of these. So they'll react completely, and we get 0.08 moles of our A minus. So you can write that all out if you want to, or you can just know you have the same number of moles of conjugate base at the end, at the equivalence point that you had of acid at the beginning. So we've got 0.08 moles of A minus. Now we have to ask ourselves, what is A minus? Well, it's the conjugate base of a weak acid, which means that it itself is going to be a weak base. And what do weak things do in water? A weak base is going to react by the Kb equation. So A minus plus water is an equilibrium with HA and OH minus. So it's going to make a little bit of OH minus here. And that's how we'll find our pH. And because it's a weak base, we're also going to need to know what the value of Kb is. They told us the Ka, so we can use our conversion Kw over Ka. So that's 1 times 10 to the minus 14th. And the Ka was 1.77 times 10 to the minus 4th. So our Kb is going to be 5.65 times 10 to the minus 11. Okay, so now I'm going to be doing this rice table with my base. There's a trick here because in my rice table, I'm not using moles, I have to use concentration. So I've got my 0.008, this is my moles that's left over, but I've actually changed the volume. I started with 80 milliliters of my formic acid, and now I've added 40 milliliters of NaOH, so I'm going to divide by 0.120 liters, and that's going to give me my concentration, which is 0.0667 molar for my A minus. And that's what we have to put down here as our initial value. Oops. 0.0667. And we're going to lose a little bit of that as it reacts with water. We're going to gain some of the conjugate acid and some hydroxide. And then we'll have our Kb, 5.65 times 10 to the minus 11th. That's going to be x squared over 0.0667 minus x. And we just have to solve for x. We can neglect this guy here. And we're going to get for x here 1.94 times 10 to the minus 6. And that's going to equal our concentration of OH minus. And so we'll take the negative log and we get the POH equals 5.71 and our pH equals 8.29. Okay, so we've got 8.29 for our pH now at step E. Good. Let's do the last one. This is when we've gone past the equivalence point. No, I'm going to stop and I'm going to talk one more thing about this. We're at the equivalence point. We calculated a pH that's slightly higher than 7. We have to ask ourselves, does that make sense? And yes, it does, because we know that we started with a weak acid, so we've ended with a weak base, so we expect that the pH will be higher than 7. It'll be a little bit basic at the equivalence point. Okay, now the last question is, what is my pH after adding 60 milliliters of NaOH? So again, I've got my BCA table. My OH minus is going to react with my weak acid. We're going to make H2O and our conjugate base. We have our 0.008 moles of HA. That's our 80 milliliters of 0.1 molar. And then we've got 60 milliliters of 0.2 molar NaOH that we've added, which is 0.012 moles. These will react completely as much as they can. So we get 0.08 moles reacting. And this is what we're left with at the end. We have now a strong base mixed with a weak base. And these are moles, not molarity. So whenever we have a strong base and a weak base mixed together, we can basically ignore the weak base. The strong base is going to dominate that whole conversation about what's happening there. And if you think about our weak base in this instance, remember our Kb was like 10 to the minus 11. It was very small. And so this is, it's going to make sense that most of our OH minus is going to come from our hydroxide that's actually just extra hydroxide we've added. So we've got 0.004 moles. We have to make sure we turn that into concentration. So we've added 60 milliliters of NaOH, and we started with 80 milliliters of formic acid. So we've got 0.14 liters. And that gives us our concentration of 0.0286 molar hydroxide ions. And we can take the negative log to get the pOH, 1.54, and our pH would be 12.46. Okay, so that's the last step here. Remember, after we've passed the equivalence point, our pH is going to be determined primarily by the concentration of our excess hydroxide ion from the base that we've added. And hopefully this is helpful. So I'll stop sharing here. Hopefully this is helpful to see that whole problem worked out and get a sense of how we do that weak acid, strong base titration. I have another example problem that's in a different YouTube video for you. So look for that weak acid plus strong base YouTube video, and you can see a different problem worked out for you. I encourage you to do several of these where you just practice doing them over and over so you get the hang of it. Remember, you've got to deal with strong things first. Strong things react stoichiometrically, strong things dissociate completely. And after you deal with that, then you can think, what do I have in my beaker? If you've got something weak, it's going to be an equilibrium or a buffer. So that summarizes everything that we did there with a weak acid titration. Here's another example for you. Thanks. Have a good day.